So tuning parameters and hyperparameters. So in this skeleton, we've got this tune length 3. In the outputs from our M1 model, we saw a little bit about that max depth parameter. And so we'll just go into detail about what that means and what we need to be thinking about. So max depth in terms of this R part 2 model. So just to break that down a little bit, R part is a word for a type of decision tree, and the 2 is the parameterization in terms of hyperparameters. So R part 2 uses max depth, which is, I'll explain in a second, which is it's easier to explain. There's also a method just called R part, which uses, instead of max depth, it uses something slightly different. So the max depth is how deep the tree is. So this is like, I'm not quite sure how you count it, but it's like 1, 2, 3, 4, 5 layers deep or something like that. So we can see that changing that max depth parameter, we can sort of imagine that there's no direct, obvious way for the tree, for a tree model to fit that kind of directly from the data. There are sort of some methods, but broadly, for a simple tree, there's no way for it to know when to stop splitting. So you define that beforehand. You can see that as you add more layers, sort of a deeper tree, you're getting a more complicated model. You've got more parameters. You've got sort of more cut points and wigglier lines, potentially deeper interactions. So so we call this a tuning parameter or a hyperparameter, and it's kind of any parameter that can't be learned directly from the data. So we have to set it sort of manually before we fit a model. And in particular, it's ones that you can't sort of know what the good values are before you start running things as well. So that, but yeah, there's some sort of there. So this is all related to regularization, which is any process that forces a model to be simple. So if we set max depth to be 3 or whatever this is, 3, we've sort of put a hard cap on the complexity of the model, and we forced it to be simple, sort of before model fitting. And there's lots of reasons we might do this, and we'll sort of carry on and go through them all in a bit. But so we've got these different values of max depth, and we don't know beforehand which ones will be good. So what we do is we try a number of values. So in this case, the tune length argument, what it's doing is saying take 3 or 10 values of the tuning parameter and fit models for all of those values, and then compare them to the holdout data and see which one performs best. So what this plot is, this is the plot you get if you just do plot of your M1 object. On the y-axis, we've got the mean absolute error, so how good our model is. High is bad, high is lots of error, low is good. And then along the x-axis, we've got our tuning parameter, which here is the max tree depth. So we can see that depending on which value of the parameter is, we have different amounts of error. So kind of unsurprisingly, as you go from a very, very simple model and add a bit of complexity, your error decreases. And then you get to this point, which is where the kind of lowest value is. And then it's less intuitive here why the error would start increasing again as you make the model more complex. And we'll go into that, why that is in a minute. But so this is how we choose tuning parameters. We just try a bunch and then select the best one. So when we were talking a bit about outer cross-validation loops and how you might try hundreds of models, this is how you can very easily end up trying hundreds of models, is by, you know, if you've got 2 tuning parameters and you're trying 10 values for each, you can easily try 100 models just of one type of model. You're not even looking at different types. And some of these algorithms are quite noisy, for example, so one of these might just fluke doing quite well. So that's the sort of driving force behind those outer loops. So we can think of a bunch of other tuning parameters that maybe some of you will know more from other sort of bits of statistics you've learned through the years. So in stepwise regression, so for people that don't know, that's where you fit a model with lots of covariates, and then you say any covariate where, say, a p-value for that covariate is whichever way around it is, but it's a non-significant covariate. You then drop that covariate and then refit the model without it. That's called stepwise regression, but you have to have this cutoff. So typically we might say that we need a significance value of 95% for us to retain that covariate, or anything, I'm going to get these the wrong way around, whatever, anything insignificant at the 5% significance level gets dropped. However, that's not some kind of, that 5% isn't some thing that reflects reality in any way. It's an arbitrary number made up by some old white eugenicist 100 years ago. So instead of kind of just making it up and guessing and just choosing a number, we might want to tune that parameter and try a bunch of different values. For people that have used GAMs, we often have like this degrees of freedom parameter that determines how wiggly the GAM is. Gaussian processes typically have like a length scale that again determines how wiggly they are. Or if we're using Bayesian models, and if you've got a prior on the kind of the regression coefficient for a particular covariate, often that might be a zero mean prior, and defaults in many software would be a very diffuse prior, but that prior can become sort of stricter and stricter around zero. And again, the strength of that you might consider a tuning parameter sometimes if you're not fitting it in a kind of very Bayesian a priori way, you might sort of just tune that parameter. So yes, we said, I think it's quite unsurprising that as the model gets a bit more complicated, our error decreases, because we're just fitting closer to the data. We're capturing more kind of nuance in the data, capturing more sort of structure in the data. But then there's this slightly less intuitive bit. The why does the error increase as our model gets even more complicated? So this is called overfitting, and more generally we sort of refer to the bias variance trade-off. I hope you can see these lines. So each of these plots, what I've done is I've randomly resampled the data set we're using, and I've plotted. I've done it the wrong. I should have done it the other way around, shouldn't I? Anyway, by accident, I've got thickness on the y-axis and survival time on the x-axis. And for each plot, I've fitted a red linear model line just for this one covariate, and I've fitted a blue smoother line. I think it's just lowest smooth is the default in ggplot. It's slightly dark blue, it's kind of hard to see, but each of these plots has got a wiggly line. So what we can see here is that these wiggly lines are very different each time. So just resampling the data and fitting exactly the same type of model, we've got a very different relationship between the two covariates. And what's happening is just this very flexible wiggly line is just fitting to the noise in the data. And so that's called overfitting. And it's called a high variance model. So the variance there is that there's a high variance in our predictions when we resample the data, or small changes in the data gives us very different predictions. On the other side, we've got these red lines, these linear models. We can see that resampling the data, these linear models are nearly all the same. They're all sort of a straight line going pretty much downwards about the same rate. So this is a model that isn't high variance, but the downside is we're always getting it wrong in the same ways. So we're always slightly under predicting these low values, for example. And so we call this a biased model because you can make a bunch of changes to you can resample the data a bunch of times and you always get the same wrong model. It's biased. Or we also could refer it to underfitting. It means it's not flexible enough to capture the complexity in the data. And so here's an example of what might be a reasonable balance between the two. instead of a very wiggly red line or a very wiggly blue line or a very straight red line, we've got a sort of a little bit wiggly line. Resampling the data, we get broadly the same relationship each time, this kind of swoopy, curvy thing, but it is flexible to capture enough, to capture some of the sense that this isn't a linear relationship. There is a bit of a swoop, but we're not just fitting to noise, we are fitting to kind of real underlying relationships in the data. So this is kind of the sweet spot between a biased model and a high variance model, the sweet spot between a overfitted model or an underfitted model. And this is here. This is the sweet spot for this R part model, is a max depth of 5. If you have more than five layers in your decision tree, you just start overfitting the model. You're fitting to the noise in the data rather than fitting to the sort of real underlying relationships. If you're less than 5, you're just fitting overly simple models, and you're not capturing some of the important and real kind of structure in the data. And so this is why it's so important to tune these models. There's no way of knowing beforehand that 5 was the right value here. We just had to try a bunch of tuning parameters and see which one works best.